To summarize, the key ideas: probability measure is positive, is normalized, is additive. And in the context of discrete spaces, everything simplifies. So to summarize what we have learnt, in discrete settings, to begin, atoms, singleton events, events consisting of single sample points, carry mass in discrete spaces. These atomic probabilities, let us say that we identify a particular outcome omega k. The atom consisting of omega k is allocated a probability that we call lowercase p of k. As k varies, as we run through all possible sample points, we determine a function of the integers. This function is called a mass function or a distribution. And it will suffice for us to check to say that the mass function is A, positive, and B, properly normalized. These are the sanity checks we'll always run through. Once we have this under our belt, then we put together event probabilities. We construct a probability measure, a set function on events, by simply appealing to the additivity axiom. Any event, let's say an event consisting of the k1th outcome, the k2th outcome, and so forth, has probability allocated to it, obtained by summing the atomic probabilities corresponding to k1, k2, k3, and so forth. Additivity rides to the rescue. Additivity now gives us a trite computation of probability measure. Occasionally, depending on the particular functional form for the mass function, it turns out we have nice and elegant analytical expressions for such probabilities. At other times, we'll have to be satisfied with numerical evaluations of these probabilities. But in all cases, we now have a complete and satisfactory construction, which gives us probability measures in discrete spaces. Now, for the first half of this class, an understanding of probability measures in discrete spaces will suffice. We can build a very rich and vibrant theory already with this understanding. But of course, eventually, we will want to move on to even more complex settings. Part 2 of this tableau shows how one could move from the discrete settings to non-discrete settings to continuous settings.